Hello friends, I'm Vivek Tiwari, your class instructor for this subject, that is material science and metallurgy. You know that we have been discussing about the unit number 4, that is ferrous, non-ferrous metals and material testing. I would like to draw your attention towards the things what we have completed. So if you see in the last lecture, that was for around 20 minutes, we have discussed about the ferrous metals, and under that we have discussed some of the introductory basics about metals, and then we have discussed about basically the stainless steel and its 4 types. I'll just quickly run over through the PPT what I had taught in the last session, and then we'll go ahead with the next topic, that is the tool steels, high strength low alloy steels. Then we'll be seeing what are the effect of the alloying elements on the steel, and then we'll proceed our discussion trying to learn about the another category of ferrous metal apart from steel, that is cast iron, and under that we'll be seeing the 4 types of cast iron, that is gray, white, malleable and SGI iron. Further, in today's class we'll start with the non-ferrous metals also. We'll start with the non-ferrous metals description, and under that we'll be seeing aluminum and its alloys, the properties and applications. So I'll just go quickly with the slide what I had shown in the last class. Yes, this is the classification of engineering materials. You know that engineering materials are of basically 4 or 5 types, and under that metals and alloys plays a very important role. Metals and alloys can be further classified into 2 types. All those things we have done or studied in the last class. Then we have seen the iron carbon diagram. Here I had told you to remember the following important points, that is the A3 line, A1 line, CM line, austenite phase, ferrite phase, all those things. Then we had seen some of the introductory concepts about the metals, why it is so much useful in industries. Then we had seen that metals, and in particular ferrous metals, can be classified into 2 types. One is steels and the other one is cast iron. And steels can be again classified on various properties or various reasons. One of them is based upon the amount of alloying elements it contains, and likewise steels can be classified as plain carbon steel or alloy steel. These things we have studied in the last class. The important type of steel called as the stainless steel was what we had discussed in the last class, and we had seen its various 4 types. That is, one is the martensitic stainless steel. Here you should remember that it is a stainless steel which shows this martensite phase at room temperature, hence the name martensitic stainless steel. Its applications. The next one was austenitic stainless steel. Here you should see that or remember that this type of stainless steel shows austenite phase at room temperature, and you should remember its basically the advantages, properties and the applications. The next type of stainless steel we had discussed was ferritic stainless steel, and here you should remember that this type of stainless steel shows ferrite phase at room temperature and its applications. Then we had also studied about the 4th type of stainless steel, that is the precipitation stainless steel and its applications. Today we are going to learn about next type of steel called as the tool steels. You know that tools are used to deform or give metals a permanent shape, and tools are required to be very hard, tough and wear resistant. Further, a tool is also required to sustain or withstand high amounts of load, and even sometimes the tools have to work or perform at high temperature applications. So for all those applications or this type of applications, we require a special type of steels, and that type of steel is called as the tool steel. A tool steel is one which basically contains the following metals. The one is carbon, magnesium, tungsten, chromium and vanadium. You know from the basics that as you go on adding carbon to any metal, its hardness and brittleness or toughness increases, and same is the case with the tool steels also. So here we add an enormous percentage of carbon to increase its hardness and wear resistant properties. So tool steels can be further classified into 4 types, that is cold working tool steels, which are basically used to deform the steels at cold working temperatures. Hot working tool steels, wherein the tools are made up of the steels which can work at high temperature applications. Then there is high speed tool steels. These are the steels which are to be used for making of tools at high speed applications. And then there are some type of steels which are used for making of tools and are called as special purpose tool steels. Yeah, so we will go ahead with the first type of tool steel called as a cold working tool steel. You should remember that this type of steels are used for making of tools wherein you have to deform the steels at cold temperature applications or cold working. What is this cold working and hot working? Cold working is one wherein you are deforming the metal at room temperature and slightly above to that, maybe around 400 or 500 degrees Celsius. This temperature at which the transition from cold working to hot working goes depends upon the particular metal. For example, for steel, the temperature at which the transition from cold working to hot working happens at 723 degrees Celsius. So the type of steels which are used for making of tools to deform the metal at cold temperatures or cold conditions is called as the cold working tool steels. So it's written highlighted on the screen also. These type of steels are used for making of or used during cold working, and these cold working tool steels are manufactured by the following three methods, that is they can be hardened, oil hardened or air hardened. So based upon this different type of hardening, these type of steels are used in prepared. One thing you should remember that this cold working tool steels shouldn't be used for high temperature applications. If you are using it for high temperature applications, you will see that this type of steels will become soft. They might warp, that means they will lose its dimensional accuracies or dimensions, and it might distort. Examples for the cold working tool steels are the chisels, hammers, drills, dies. This type of tools you have used in your basic workshop lab. So this is about your cold working tool steels. Just opposite to this is the hot working tool steels, wherein the steels are used to make the tools which are going to work at hot working conditions. So these are used for working of steels at high temperature applications like stamping, upsetting, extruding, piercing. There are n number of metallurgical operations wherein you are deforming the shape of the metal at high temperature applications. For example, there is forging, there is rolling, extrusion, drawing. These are all the processes at which you heat the metal, and at that time you deform the metal. And for deforming the metal at high temperature, you have to make use of this type of steels, that is hot working tool steels. The important feature of this steel is that they do not harden, they do not soften at high temperature, they do not become soft at high temperature conditions. And this type of steels are used for making even the aluminum dies, the magnesium dies, forging dies, etc. So this is about your hot working tool steels. The next type of tool steel is your high speed tool steel, which is used which maintains its hardness even at high speed and even at high temperatures. And there are two type of high speed tool steels. One is tungsten, which is also called as the T series, and the other one is the molybdenum steels. So this type of steels are used where high speed operations are there. For example, if you are rotating the steel at very high temperature, in the case of your lathe machine or VMCs, at that time if you want to deform the metal, you should make use of this high speed tool steels. Then there are some kind of special purpose tool steels, the steels which are not used for the hot working conditions, even not for the low working conditions, and not even for the high speed tool speed applications. Then those type of steels get into this type of steels called as the special purpose tool steels. These type of steels are shock resistant. They are they are shock resistant and used for some special purposes. Some of the examples for the special purpose tool steels are cemented carbides, cermats. This is an important type of tool steels which is a combination of two materials. One is ceramics, CER means ceramics, and other one is MET, MET means metals. So it is a combination of two materials, that is ceramics and materials. I would like to ask all the students to go and explore few more details about this type of material, that is cermat, which is a combination of two materials, that is ceramics and metals. Similarly, there is one more type of special tool steel called as stellites, which is also very much quite famous in industries, right? So these are the different type of tool steels which are used. The next type of steel which we are going to discuss is called as the HSLA, that is high strength low alloy steel. The basic feature of this type of steel is that it contains low alloying elements, plus it has low carbon content also. Because of this low alloying elements as well as low carbon content, this type of steel shows high strength. Let us go ahead with the discussion which are written in words. These are basically low carbon steel. The percentage of carbon varies from 0.07 to 0.25 percentage carbon. Plus they have low alloying contents like titanium, vanadium, niobium and aluminum. And because of these two reasons, this type of steel shows high strength. And the one major feature or characteristic feature of this type of steel is that they show good ductility, malleability, formability and weldability. It is because of this important application of this steel, it is used in n number of applications. That is weldability. Coming to the applications, you can see the Sydney Bridge, which is made in Australia, is completely made out of this HSLA alloy only. And the basic feature which distinguishes this type of steels from the other type of steels is its weldability nature. Similarly, there are structures like the tubes for the pipelines, pressure vessels, storage tanks, big welded structures, all being made up of the HSLA alloy steels only. So these are the different type of steels which we have discussed till now. So quickly going back, we have discussed about the stainless steel, its different types, that is martensitic stainless steel, austenitic stainless steel, ferritic stainless steel and precipitation stainless steel. We have discussed about the tool steels. Under that we have discussed four types, that is cold working tool steel, hot working tool steel, then high speed tool steel and special purpose tool steels. We have also discussed the third type of steel, that is HSLA, high strength low alloy steels. And next we'll go ahead with the discussion about what is the effect of the alloying elements on the properties of steels. You have seen from the discussion that alloying elements or the elements when added to the steel, it definitely changes its properties. For example, if I talk about the stainless steel, the alloying element chromium makes the steel stainless. Similarly, addition of silicon will make or increase the machinability of the steel. Similarly, manganese or nickel when added to the steel will increase the austenite phase present in the steel. Similarly, when you see, if you add chromium to the steel, the ferrite phase becomes more dominant and stabilized. So this leads to a conclusion that alloying elements or the elements being added to the steel definitely affects its properties. So we'll try to explore a little bit more about that. See, whenever we add the alloying elements into the steel, alloying elements has two-fold effects. One is that it will affect the iron carbon phase diagram, its iron carbon phase diagram, and second one is that it will affect its properties. How does it affects the iron carbon phase diagram is that whenever we add some kind of alloying elements to the steel, it will increase the area of austenite or ferrite, and in other words it will increase or decrease or upper or lower the A4, A3 or A1 line temperatures. I will explain you more about that when I come to the iron carbon diagram. However, these alloying elements which are there can be broadly classified into two types. One is the elements or the alloying elements which stabilize the ferrite phase, and examples are chromium, tungsten, molybdenum, vanadium and silicon. And those are another sort of elements are there which will stabilize the austenite phase in the iron carbon diagram, and examples for that are manganese, nickel, cobalt and copper. I hope you remember the ferrite stainless steel. I had said that the basic element present in the ferrite stainless steel is chromium, and I said that chromium is a ferrite stabilizer. Similarly, when I had spoken about the austenitic stainless steel, I had said that the major elements present in the austenitic stainless steel is manganese and nickel, and these are the examples for austenite phase for stabilizers. Here the relevance come again. Okay, so the first one is the ferrite stabilizer. These are the elements which will stabilize the ferrite phase. And how do they stabilize the ferrite phase is that here you can see the iron carbon diagram. You know that this is the region wherein the ferrite phase is present. Because of the addition of the ferrite stabilizer, you will see that this line, that is the A3 line, and this A4 line over here, or the A4 point, all go on coming down, and the effect is seen like this. Here the second diagram you can see, without the addition of any chromium or 0% of chromium or any ferrite stabilizer, the graph is like this. As you go on increasing ferrite stabilizer, you will see that this rhombus kind of structure goes on decreasing and decreasing, or in other words, the ferrite phase becomes more and more dominant as you go on adding the ferrite stabilizers. So this is the effect of the ferrite stabilizer on the iron carbon diagram. So here it's written as these elements are ferrite stabilizers. These elements lower the A4 line, raises the A3 line, and till both meet, and because of which the ferrite becomes, or the ferrite phase becomes more and more dominant even at room temperature, which is the case in the case of your ferrite stainless steels also. The next stabilizer is the austenitic stabilizers, and examples for the austenite stabilizers is your manganese and silicon, or manganese and nil silicon. I'll just make manganese and nickel. So here you can see that how as you go on adding the manganese into the steel, you will see that this austenite phase becomes more and more dominant, or in other words, what does this manganese and nickel do is that this A3 line and this ACM line are being shifted downwards, and this line also is being shifted upwards, because of which more and more and even at room temperature you will see that the austenite phase becomes dominant or present in the metal. So this type of stabilizers are called as the austenite stabilizers. So this element stabilizes the austenite phase. These elements shifts the A4 line upwards and lowers the A3 line. So A3 line will go down and ACM line also will go down, and even at room temperature we will be seeing the presence of austenite phase. So these are the two type of stabilizers. Now there is a printout for the effect of the alloying elements on the steel, which I will be sharing you by taking a photograph and sending you in the form of a WhatsApp. Okay, so this completes basically the all the discussions about the steel. You know that metals or alloys can be broadly classified into two types. One is ferrous metals and non-ferrous metals. Ferrous metals can be further classified into two types. One is steel and the other one is cast iron. Steels are one wherein the percentage of carbon is from 0 to 2%. Cast iron is one wherein the percentage of carbon is from 2.1 to 6.67%. Under steels there are 1000 type of steels. However, we have discussed about a few important type of steels, that is stainless steel, tool steel, high strength low alloy steel. I would again ask the students to explore few more steels and its properties. Then we have discussed how does this alloying elements affect the properties of steel. We have seen that there are two type of alloying elements. One is the one which will stabilize the ferrite phase and is called as a ferrite stabilizers. Another set of alloying elements will stabilize the austenite phase and they are called as the austenite stabilizers. We have discussed about these two things, and now we'll proceed with the discussion about the next important type of ferrous metal, that is the cast iron. Cast iron basically are used in castings, and hence the name cast irons. They are very much or they are comparatively more hard and brittle compared to the steel. The basic reason behind this is the percentage of carbon. You see that in the case of cast iron, the percentage of carbon is increasing, and because of which it becomes more hard and brittle. So with this basics, we'll go ahead with the discussion about the cast iron. Cast iron, like steels, are basically alloys of iron and carbon only. So they are again the alloys of iron and carbon only, just like steels. However, the percentage of carbon is from 2.1 to 6.67%. Then high carbon makes this cast iron more brittle. I have told that earlier also. And the commercially manufactured cast iron are in the range of only 2.5 to 4%. If we increase the percentage of carbon beyond 4%, then the metal will become, or the cast iron will become more brittle. That's why it is prevented, and we limit our range of carbon from 2.5 to 4% only. Cast irons can be rolled, drawn at room temperature, means it can be rolled or it can be converted into sheets. Sorry, it cannot be converted into sheets, or it cannot be drawn in wires. In other words, cast irons malleability and ductility is very low. This is the meaning of this sentence. Then they can, however, this cast iron can be easily melted and they can be casted or given a shape. That is the reason why this cast iron are basically or widely used in the foundry industries. And if you remember, if you see the iron carbon diagram, instead of cast iron I have written there castings, which means this cast iron are basically used for making of castings in foundries. Cast irons are cheap, and there are four types of cast iron which we will be discussing in the subsequent discussion. The first one is the white cast iron, which looks white when it is fractured or broken. The second one is the malleable cast iron, which is a byproduct of white cast iron, but however the properties are better than white cast iron. Gray cast iron, which is almost sometimes being confused with the cast iron term. Many of people, cast iron, for them cast iron means gray cast iron, and spherical graphite iron, which has the properties similar to that of the steel. So these are the four types of cast iron which we are going to discuss in today's class. The first one is your white cast iron. White cast iron is also called as white iron because when they are fractured, the fractured surface will show white surfaces, and it is the only type of cast iron wherein the carbon is present in the form of carbides. Here you should remember that the presence of carbon in the cast iron can be of two types. One is either it is in the form of carbide, or otherwise either it is in the form of graphite. So in white cast iron, carbon is present in the form of only carbide. So this is the sentence been written. White cast iron, also called as white iron, it is the only member of cast iron having carbon as carbide. How they are produced? They are produced by chilling selected areas of the cast iron, preventing graphite formation. So here this means that if you want to prepare white cast iron, you have to melt the iron and you have to do the casting process. However, when you are doing the casting process, you should cool it immediately, or it's also called as chilling. Because of doing that, you will see that the iron turns out to be white and it's called as white cast iron. The properties of white cast iron is that it is extremely brittle and it is very difficult to machine. And that is the reason why white cast iron basically finds its application in compressive type of loadings, wherein compressive loadings have to be taken much. For example, liners of the cement mixers. You know that cement mixers are their linings are being made up of white cast iron. Even the ball mills, wherein the ball bearings and all are being made up of this white cast iron itself. And the other properties are that they show very high resistance to wear and other things also. So this is the microstructure which is shown on the screen. This is a white cast iron, and this is a casted component of white cast iron. You can see that they look white in color. So this is the important features of the first important type of cast iron, that is the white cast iron. The second type of cast iron is the malleable cast iron, which is a byproduct of white cast iron. So that is what is written on as the first sentence. This cast iron is obtained from white cast iron. Here the carbon is present in the form of graphite. In the earlier case, I had said that the cast iron is present in the form of carbide. Here it is in the form of graphite, and whenever there is the presence of carbon in the form of graphite, it gives out a black color, a little dark color to the cast iron, and that's why the fractured surface of a malleable cast iron, or even in the case the next few cast iron what we are going to discuss, will be dark in color. And the properties of malleable cast iron are just opposite to that of white cast iron. That means they are malleable, they are not brittle, and they are used in applications where tensile loadings are also being applied. And hence, if you see the application of the malleable cast iron, they are used in making of flanges, valve parts, etc. This is the microstructure of a malleable cast iron. Okay, so and these are some of the examples or the places of applications of malleable cast iron. The next type of cast iron is called as the gray cast iron. It is the widely used type of cast iron, and it is the oldest form of iron. Many people confuse gray cast iron with the cast iron. Gray cast iron is named because a fractured surface of this type of cast iron will show grayish fractured surface. So that's being written as a third sentence. Gray iron is named so because its freshly fractured surface has a gray appearance. Here the cast iron contains graphite. You know that I had said you earlier only that this type of cast iron will contain carbon in the form of graphites, while white cast iron contains graphite in the carbon in the form of carbides. Here it is in the form of graphite, and this graphite is present in the form of flakes. This is depicted from the microstructure what you can see over here. Here the carbon is present, these are the presence of carbon, and this carbon is present in the form of hairy flakes. So this is the understanding what I wanted you to understand. And because of the presence of the carbon in the form of flakes, it shows good amount of tensile properties. However, one disadvantage of this flakes in the form carbon in the presence of flakes is that these flakes acts as the point of stress concentrators in the metal, which means these are the points through which the stress will get concentrated in the metal, and it will result in the fracture of the metal. That's why the morphology, the shape, the size of these graphite flakes play a very important role in gray cast iron. There is a level beyond which if the graphite flakes are present in the metal, then it is disadvantageous, and it is usually not taken or not used in the industries. Okay, so yes, here if you go through the slides you will understand it more clearly. Presence of flakes in the iron makes them good machinability and good damping property. Graphite flakes are the stress concentrators. Gray cast iron is widely used in the machine bases. You might have seen basis of machine, they are made up of this grey cast iron only. Engine frames, then drainage pipes, pump housing, etc., which requires good compression bearing capacities. And if you see the microstructure of the grey cast iron, it will show the flakes of graphite with the pearlite matrix. So the background is the pearlite matrix with the graphite flakes. These are the examples of the grey cast iron wherein they have been used in applications. The next type of cast iron is the spherical graphite iron. These are also known as ductile iron or nodular cast iron. You should be knowing that this type of cast iron is also known as ductile iron or nodular cast iron. Here the carbon is present in the form of graphite, of course, and it is in the form of tiny balls or nodules. Here you can see the microstructure of a spherical graphite iron. You see that the carbon is present in the form of tiny balls or nodules, and this is the reason why this type of cast iron shows good tensile properties as compared to the previous one, that is the grey cast iron. Grey cast iron, the carbon is present in the form of flakes, which reduces its tensile strength in fact. And in the case of your spherical graphite iron, since the carbon is present in the form of nodules, its tensile strength increases. In many places, spherical graphite iron is taken or used similar to that of the steel. Hence this type of steel cast iron is very much important. The importance lies here is that although it is a cast iron, its properties are just similar to that of steel, and that's why it is used in industries. Okay, so they are produced from grey cast iron by adding of magnesium. SJ iron unpopular due to its improper properties. They combine both the advantages of cast iron and steel. If you see the microstructure, it will show the spherical graphite nodules plus with a background of matrix. They are used in the making of crankshafts, automobile door hinges, piston, cylinder heads, motor frames, etc. So these are the four types of cast iron what you should remember. Now so here we complete our discussion about the ferrous metals. Under the ferrous metals, I'll just go quickly have an overview of what we have discussed. We have discussed about the stainless steel and its types. We have discussed about the tool steel and its types. We have discussed HSLA. We have discussed about the cast iron. And we have seen the four types of cast iron, that is grey cast iron, white cast iron, malleable cast iron, and spherical graphite iron. In the examinations, you might be asked about the microstructures, and you might be asked to identify the type of cast iron it is. So you should remember that the grey cast iron